All right, good afternoon, everyone. Right, we'll start the class here. So we are missing a few. Right? Yeah. We'll start the class, and we'll continue with some of the questions we have done in the previous part as well. So, shall we start with a discussion of one of the Born-Haber cycle questions we have done in the past? So, tell me, were there any questions that you specifically found difficult in the Born-Haber cycle related questionnaire? Or did you attempt it at all? That's what I want to know. Born-Haber cycle related questions. Did you do them? Did you go through them? Right? Shall we take a look at a question where you have to draw the Born-Haber cycle? They have, in all of these questions, they are guiding you little by little to draw and complete the Born-Haber cycle, but you should be able to draw Born-Haber cycle on your own as well. So, shall we start with question number 3? Right? Question number 2 seems to be somewhat easy. Question number 3, what about that? Did you do question number 3, Born-Haber cycle? Yeah? Right. So, let's focus on this. They say the table shows energy values used in Born-Haber cycle for magnesium chloride. The complete Born-Haber cycle for magnesium chloride. Complete the Born-Haber cycle for magnesium chloride by adding labels for each of the 4 energy changes and writing formula in 2 empty boxes. So now they have actually completed halfway. You have to complete the rest. So when it comes to this magnesium chloride related question, we have Mg solid as well as chlorine gas. That is the starting point on the Born-Haber cycle. Right? We are starting here. And then what do you think is present in the box here? Oh, at this level, what did you write there? Sorry? You turn the magnesium into a gas. Okay, so what was the enthalpy then? What was the enthalpy here then? Out of the given answers, they have given enthalpy change of atomization of magnesium, enthalpy ionization of magnesium, and all of them again. So what should be this? Delta H atomization, AT of magnesium. And then what did you draw here? What did you write here? You wanted to do, you can see somewhere up above, now they have 2 empty boxes, this one and this one. And then in the 4th one they have written magnesium 2 plus gas and Cl2 gas. That means we haven't atomized chlorine. Right, we haven't broken the bonds in chlorine or atomized chlorine here. So that means we are talking about ionization, because you have to take this into magnesium 2 plus. So that would mean we are talking about first ionization of magnesium. So if you can figure that out, that's good. Right, IE1 of magnesium. And then this would be IE2 of magnesium. Right, and afterwards we have 2 electrons. Now this will release 1 electron, and then after the ionization we have 2 electrons here. You have to make sure that every stage is perfectly balanced, and then the next stage is magnesium 2 plus ions along with Cl gas. That means we have turned chlorine into gaseous atoms. Right, so there are 2 electrons here still, and they have given you second ionization energy of magnesium and change of atomization of chlorine, enthalpy change of atomization of chlorine. So how many chlorine atom molecules are, how many chlorine atom moles are formed here? Altogether 2. So did you just write atomization of chlorine, or did you multiply it by 2? What did you do? You did multiply it by 2? You forgot that? See, I told you some might. Why? Because bond enthalpy talks about this formation of 2 moles of gaseous chlorine atoms by breaking 1 mole of bonds. This is delta H D. And then atomization of a gas means it's focusing on forming of 1 mole of atoms. You have to remember the definitions, right? The definition is the key here. Without the key, you will find it difficult to get to the answers. So then afterwards, we have now these turned into Cl1 minus. Here we have magnesium 2 plus gas plus 2Cl1 minus gas. And at that point, we have come all the way down here to the formation of magnesium chloride solid. Magnesium chloride solid. This is going to be delta H formation, and this is going to be delta H, that is formation enthalpy. That is formation. From here to here, that is formation. If you were going the other way around, that is dissociation enthalpy. Is that clear now? Right. So after drawing this, did you find the enthalpy change correctly? Is there anyone who actually calculated the proper enthalpy values? Right? Can someone tell me the answer they got? Anyone? Minus 314. 48. Right. Did anyone else get minus 348? Right. So that seems to be the answer. We will still calculate it and see. We have now all of these enthalpy values are adding together. So we can write Hess's law. We can write delta HF of magnesium chloride is equal to delta HAT of magnesium plus delta H first ionization energy of magnesium. So I'm just writing these symbols, but you should write it the correct way with the proper indication of what enthalpy we are talking about. Since I'm not writing it correctly here, it's not a good example, so we'll write the correct values. Delta HF magnesium chloride solid is equal to delta HAT magnesium solid, and then everything is adding up here. So since I don't have the space here, I will write it here, plus delta HIE1 of magnesium and plus delta HIE of magnesium. Now at that point we write magnesium plus gas plus delta H atomization of chlorine. Now this is IE2, chlorine gas into 2. This one is multiplied by 2 plus yeah, that's it, and plus finally delta H formation in the lattice energy of magnesium chloride. Now we have to add all of these, and that will be equal to this. So altogether we have 1, 2, 3, 4, 5, 6. I have missed a few, I think. Bear with me. 1, 2, 3, 4, 5. Which one have I missed? After atomization, I have missed the electron gain plus delta H electron gain Eg1 of R. Here also, now I haven't written it here, delta H electron gain 1 multiplied by 2, because there are 2 chloride ions formed here, not just one, right? So you have to multiply that as well by 2. Cl gas. Now you are done with writing this as a cycle. You can substitute the values. So when you substitute the values, delta HF happens to be formation enthalpy of magnesium chloride is minus 641. That is equal to enthalpy of atomization of magnesium plus 148 plus 738 plus 1451, 122, and then lattice enthalpy is going to be, oh, bear with me a second, students. 738. Second ionization of magnesium is 1451, and then we have atomization of chlorine. So atomization of chlorine is going to be 122. Enthalpy change of atomization is plus 122. So we have to multiply that by 2 and write. So that will be 244 plus enthalpy change of formation of magnesium chloride is given. Lattice energy is also given to you. So you are trying to find the electron gain here. Right. So lattice enthalpy is minus 2526. The only thing that we don't know is delta H Eg1, and there's 2 of them. So that is what we are trying to find. And when you're trying to find it, as you say, what is the answer you said you got was? Minus 348 kilojoules per mole. Is that understood now? Clear? Right. So this is how you normally get to the answer. So you should be able to figure out whenever a Born-Haber cycle is given to you, how to get to the answer. So only thing that you don't know is this. You can rearrange the equation to isolate this, and at that point you'll get to this answer. Clear now? Right. So that is the main thing you need to know when it comes to Born-Haber cycle. If you have done questions and if you are still having some doubts about these questions, let me know. And I am going to give you some tunes here with the past paper questions, because we need to do some past paper questions as well. So we will attempt some past paper questions today, and the same questions that I have given to you are there in the back of the tute as well. But MCQ questions and some of the essay questions are there in those tutes. Is that clear now? Now, if this is clear, we can move on to an actual past paper question. Now, question number 5 usually happens to be, question number 5 and 6 both are usually physical chemistry questions. Now, enthalpy is a physical chemistry part. So, question number 5 and 6 both are physical chemistry question. Usually those students, question number 5 A part or question number 5 B part happens to be enthalpy question. Is that clear? Majority of the time, question number 5 B part happens to be enthalpy type question. So if you, now unfortunately I forgot to number these pages. Right after all of the MCQs, we come across one of the enthalpy type questions in question number 5 here. Do the B part, because the A part is equilibrium and gas laws related question. Do the B part, which is the enthalpy question. Attempt that question, please. Yeah, liquid heptane undergoes complete combustion as follows. That question. Using the information given below, calculate the standard enthalpy of formation of liquid heptane in kilojoules per mole. We can do part by part. Shall we do the part 1 first and then the part 2 later? So then it will be a bit quicker. Otherwise, we'll have to wait till all of you are done with the entire thing. Shall we do part 1 first? B, part 1. That's a very easy one. Quickly do it, and I will discuss it afterwards. Now, just to get an idea, we will start doing this question together now. So the question says, using the information given below, calculate the standard enthalpy change of formation of heptane. They have only given you combustion enthalpy of heptane, that is given to you, and then rest of the enthalpies are carbon dioxide formation and water formation enthalpy. So the main equation that was given to you, there's only one equation that is given to you. So if you like, you can start with that, because that is also way that we can actually start the question. So I will start the question here. I'll draw the Hesse cycle here. I'll divide the board into two, otherwise it will be difficult. So we have heptane, C7H16 liquid turning into with actually 11 oxygen molecules. You are forming 7 carbon dioxide along with 8 H2O liquid. So this is gas, that is liquid. So we have 14 oxygens, 14 oxygen plus 8 oxygens altogether is 22 oxygens. So that is why we have 11 oxygen molecules here. Now this is the combustion enthalpy. This is the combustion enthalpy of liquid heptane, and they have only given you formation enthalpy of carbon dioxide and water. So basically these two we know how to form. So let's write their formation enthalpies here. You can draw the Hesse cycle in many ways. This is one of the ways in which you can do it. So we can write carbon, solid, graphite. We need 7 of these, plus we'll need oxygen. So we write O2 gas. Since we are forming both this as well as water, we will be needing exactly 11 O2 molecules. And apart from that, we'll be needing hydrogen gas. You will need exactly 8 hydrogen molecules. Do we need anything else? No, we have 7 carbons, 11 oxygen molecules and 8 hydrogen molecules. So these together will form 7 carbon dioxide and 8 water molecules. Clear? So we can even identify what these are. This is the formation enthalpy of carbon dioxide. Formation enthalpy of, let's say, carbon dioxide gas. Now how many carbon dioxide molecules are formed here? 7. So therefore we have to multiply that by 7. This is the formation enthalpy. This corner one is the formation enthalpy of water. Since we are forming 8 water molecules, we have to multiply that by 8. And then this happens to be the formation enthalpy of 1 heptane. Right? So we have drawn a cycle, it's a cycle, and at each level this is balanced. So therefore we can now write equation. We have delta HF C7H16 liquid plus combustion enthalpy of C7H16 liquid is equal to 7 delta HF of carbon dioxide formation enthalpy multiplied by 7 plus water formation enthalpy multiplied by 8. Now we can substitute the values here. The values that are given to us. For the combustion enthalpy, it is minus 4850. So formation we don't know, we keep it as it is. C7H16 liquid plus 4850 50 kilojoules per mole equals, we have this 7 carbon dioxide formation enthalpy. So we have 7 multiplied by minus 393.5 plus minus 285.8 into 8. Is that clear? So now when you do this, we are forming delta HF C7H16 liquid is equal to, now first of all, can someone tell me what you got when you multiplied these values? We can do the multiplication here, but I don't want to take the time to do it here. These are simple multiplications, so I'll quickly get you the answer. 285.8 multiplied by 8. So the answer happens to be, for these ones, it becomes minus 5040.9, and there was this minus value, we send it to the other side, then it becomes plus 4850 kilojoules per mole. So when you solve it, it should be 0.9 will remain, 0 here, and then 14 minus 5 is going to be 9, and 190.9 kilojoules per mole. Did you get to this value? Anyone got to this value? Very good, right? So if you have gotten to this value, that means you have drawn the Hess cycle correctly, and you have not missed the multiplications. There were 7 carbon dioxide and 8 water molecules. You have not missed any multiplication. If you have gotten to this answer, answer is this. Correct your answers if you have gotten anything different to this. And after this, attempt the second part of the question. Do the second part of the question. Now I will give you 7 minutes to do this. Usually the entire structured question can be done in 15 minutes. So for the B part, you have about 7.5 minutes. So this has to be done, like the entire question should be done in 7 minutes. Let's keep the half aside, right? Now you must be done by now, right? The most interesting part of the question is this. Did you find the neutralization enthalpy to be minus 54.6 kilojoules per mole? Or any of you got to this value? You got to this value. So now this is a point that I've been wanting to talk to you about. That is, now once you have found the amount of energy that is released, we can calculate the enthalpy change. Now this is something you have to learn how to do. So imagine when this, now first of all I'll discuss the initial bits later. Those are basic theory parts, but I want to talk about what is happening here. They have mixed 200 milliliters of HCl, 200 milliliters of sodium hydroxide. Can you remember the neutralization enthalpy definition? And as I was giving you the neutralization enthalpy definition, I highlighted something. Whenever strong acid strong base reacts, neutralization reaction takes place. Can you remember what was the neutralization enthalpy? I asked you to remember that also for water. What was it for neutralization enthalpy? The standard neutralization enthalpy, there was a specific value that was given. Okay. Per mole of water formed. So basically it was like when 1 mole of aqueous H plus ions, 1 mole of OH minus ions react together to form 1 mole of liquid water is the definition. So I'm asking, what was the enthalpy change? I asked you to remember that as well roughly. Minus 57 kilojoules per mole, right? It will not be important to remember it, but if you remember it, it will be easy to double check whether your answers are okay. Okay, right? So now what has happened is we are reacting an acid and a base. Although we react sodium hydroxide and HCl, the main reaction that is taking place is just the formation of liquid water. These are spectate ions joined together to write sodium chloride. That's it, right? So this is the main reaction that is taking place, and as this reaction happens, energy is released from the reaction. This reaction releases energy, right? And that released energy causes the solution temperature to increase. Clear? So the temperature has risen from 25 to 31.5. So we have calculated the total amount of energy that was released by the reaction. How much was that? 10.92 kilojoules, right? 10.9492 kilojoules. That's it. So I have written it again. Heat released by the reaction, just to make you understand. Although this comes as a positive value, that is because the solution absorbed energy, right? Solution absorbed the energy that was released by the reaction. Is that clear? If I am emitting heat right now, whatever that is around me should absorb that energy. So if I am the reaction, I am reacting and releasing energy, and the air here increases in temperature. Is that clear? So just like that, there is a reaction happening here, the solution increases in temperature. Clear? So that is your the amount of energy that is released here. And now after talking about this, then we move on to the neutralization enthalpy calculation. So in order to do that, we have to remember the definition. Definition says the amount of energy when 1 mole of water is starting from H plus and OH minus ions. 1 mole of water. Is that clear? So this reaction takes place forming only 0.2 moles of water. Now I calculated, like sodium hydroxide and HCl solutions, they had both 1 moles per decimeters cube concentration, and we used 0.2 decimeters cube of each solution, right? 200 milliliters of sodium hydroxide as well as 200 milliliters of HCl. So in each solution we had exactly this many moles of acid and base. So that many moles of acid and base, 0.2 acid and 0.2 base reacts to form how many moles of water? 0.2 moles, right? So when 0.2 moles of water was getting formed, this much of energy was released. Is it understood now? Is that clear? So this energy was released when 0.2 moles of water was formed. So if you want here, we can rewrite this. We can write energy released when 0.2 mole of H2O was formed, and this happens to be 10.92 kilojoules. Then you can write when 1 mole of H2O is formed, then that would be, if 0.2 moles formed releases this much of energy, 1 mole would be this much, kilojoules divided by 0.2 mole, and it comes to this value, and that value happens to be your neutralization enthalpy. And there has been a small modification done here, the negative sign. Why? Energy is released. Now whenever energy is released, delta H is negative. Is that understood now? Clear? So this negative sign should be included. If not, it is a problem. Is that clear now? It has to be 100% clear. So whenever they are talking about enthalpies, the whole definition story is important when it comes to this. For example, atomization and bond dissociation of chlorine, 2 different enthalpies. Now if they are asking you to communicate this, like energy change eventually as an enthalpy value, you have to keep it as kilojoules per mole. That means for a single mole of something, you have to remember which single mole we are talking about. Like when it comes to bond dissociation, we are breaking 1 mole of bonds. When it comes to atomization, we are forming 1 mole of gaseous atoms. So this per mole stands for something, right? So you have to remember what that something is. Is that clear? Did you get to this answer? Yeah? If you didn't, copy this one and I will explain the rest to you. Right? There are other parts that we have to talk about. We'll be getting a few questions done today because I want you to be quite okay with these parts. So after doing this, part 5 rated questions, we'll move on to some MCQs as well. Hopefully we can move on to some MCQs today. We are going to be staying here till 7, right? So we can get some MCQs done. Right? So shall we discuss the rest of the question? So the first one, explain how you would design the above experiment and the necessary assumptions to be made in the process. Now they are giving you solutions, measuring cylinders, polystyrene cup and thermometer was provided. You can say we will be carrying out the experiment in the polystyrene cup, and we'll be placing the thermometer in the polystyrene cup and we'll be closing the lid of the polystyrene cups to minimize heat loss, right? And we'll be using measuring cylinders to measure equal amounts of the solutions, and before adding them together their initial temperatures will be noted down, and after mixing them together we are going to observe the highest temperature that the reaction mixture reaches. So this is how the experiment is designed. So basic assumptions that are made are the basic main assumption is when we are using the polystyrene cup, the heat loss to the environment is minimal. Okay, and we will also have to assume all of the energy that is released by the reaction is absorbed by only the solution, not by the polystyrene cup. Polystyrene cup doesn't absorb anything. Is that understood? Actually, even the thermometer absorbs a certain amount of energy. So we assume.
Density of the solution.
Yes, and it's like this. The density part is it's a good third option, right? It's a good third option. That is that density of water, and so basically density of the two solutions are equal to the density of water itself. We do make that assumption, right? We do make that assumption. That is good, right? So make that assumption and you can write it down, because they have only given you the density of water, not the density of the solutions that are given. So we make that assumption all across, actually, all the time. So do you understand these now? Right, then we move on to the next one. What are the measurements those have to be made, that have to be made for the estimation of heat released in the experiment? So the main measurements are basically when it comes to adding these solutions together, you can mention those also, just to be on the safe side. You can mention the volumes should be measured before adding them to the polystyrene cup, and the temperature of the solutions before they are mixed together should be noted down, and temperature, the highest temperature to which the reaction reaches should also be noted down. Is that clear? Because we are trying to observe from the initial temperature how high or how low the reaction has, so temperature has reached. So after the reaction is initiated, in this case this is exothermic reaction though, so we are observing the highest temperature the reaction reaches when the reaction takes place. Is that clear? Right. And then we have the answer here for the third part. Now we have a good question here, the fourth one. The student repeated the experiment with the same volumes in question 3 by using 2 moles per decimeter cube concentrated HCl and 2 moles per decimeter cubic concentrated sodium hydroxide. So the number of moles the volume did not change, but what has he done? He has increased the concentration. Meaning what? In this area, now there is twice the number of moles of reactants. Earlier, you had 1 moles per decimeter cube. Basically, we had only 0.2 moles of HCl and 0.2 moles of sodium hydroxide. But now, we have 0.4 moles of HCl, 0.4 moles of sodium hydroxide. So, they are asking you, explain what you would expect for the value of Q, giving reason. So, what would you expect for value of Q? What could you say? Yes, you could expect the value of Q to approximately double. right? It won't be a nice clean cut doubling of the value because the heat loss will also be a bit higher. So the value of Q will approximately double. What is the reason? The reason would be the number of moles of HCl and the number of moles of sodium hydroxide in the same volume has doubled, right? So this means twice as much of the previous reaction will take place now.
So after that, therefore, delta T has also.
They are asking?
No, after that mole part, can be like therefore delta T also has increased.
Delta T doubling. Delta T will, yes, it could double. Delta T would double here. Yes, you can say that also due to the number of reactant moles increasing, delta T could double, because if this is doubling while both of these are remaining the same, that means delta T has to double, right? So you can write that. You can write that. But they are mainly asking this. What would you expect for you were explaining why Q is doubling, right? So you are explaining Q. Right, okay. Then okay, no problem. But please do mention the number of moles increasing part, right? In the same volume. And then we have the B part. Explain what you would expect for the value of delta H naught giving reasons, delta H naught neutralization giving reasons. What do you think will happen to neutralization enthalpy here? Will it double? No, like you said, it will remain the same, right? So if you have written remain the same, very good. Why? Because we are communicating this value as a per mole value. Now per mole value doesn't, it's a, what kind of property is this at that point if you are talking about a per mole value? There are two types of properties. What type of property is this? Can you remember extensive and intensive? Okay, those of you who say extensive, nobody says extensive. Intensive. Okay, I should have asked who says intensive first, right? So yes, intensive property. Clear? It doesn't change on the amount of heat that is released. It mainly depends on the number of moles. The answer is correct. Very good. And then V part. If there was a significant amount of heat loss during the experiment, how would this affect the delta H neutralization value? How would that affect the delta neutralization value, students? What would you say? What kind of a value would you get? You have to explain that. So what did you write? Will it be greater than 54.6 or smaller than 54.6? What is the answer? Yes, you can write the delta H neutralization value will be a smaller negative value than 54.6. Why? When the heat is lost here, the recorded Q value will be smaller. When that happens, the delta H neutralization value will be smaller. So heat is released to the environment, so it is not captured in our calculations because of that. Is it understood?
So I didn't mention the negative part, and I said it is greater than that.
So then that is very risky, right? When you say great, you said it will be?
Then because of minus value.
You said it will be greater.
Yeah, minus 1 is greater than.
Okay. So now when you are right to mathematically, that is not wrong. Like when you say greater than, but the thing is, keep in mind we are talking about energy values here. When you say
I mentioned that Q is less than, and then the Q is big.
Okay.
Q is less than actual Q, but because of we are multiplying it by minus 1, the inequality.
As a value, like you said, if this becomes like, let's say, minus 50 kilojoules, that is mathematically it's a greater value than minus 54, right? So you are right to say that, but again, I would prefer us being a bit, because this could mean, now greater means always the amount of energy released could be greater could also be an interpretation of what you're saying, right? So I know it is mathematically sound to say this particular value, and if you take minus 50 is greater than minus 54, okay? But it is always better to say greater negative value. Okay, if you really want to say greater than this, sorry, what was I saying? Smaller negative value. Within brackets you can write a greater value. Clear? But write both in that case. I would always prefer the negative sign being included there. Right? So is this clear now? Do you understand that part, everyone? So very good. So if you are okay with that part, this one is, now students, I'm going to time it. I can't allow you to do this for too long. So the next page, B part, I will time it for 7.5 minutes. It's like this at the exam, of course you have a little bit of leeway. Why? Imagine you do one easy question that doesn't take 15 minutes, then you have some more time to do these kind of questions. But keep in mind, I want you to be able to do it in the correct amount of time without taking additional time. So I'll give you 8 minutes, let's say. So try to get it done in 8 minutes. Are you asking about what question it is? So in the next page there is a question saying, write the respective balanced chemical equation for the following incidents happening at 25 degrees Celsius. Right, then we have the standard enthalpy of formation of nitric acid, standard lattice enthalpy of magnesium chloride. So in our syllabus, students, whenever we are talking about lattice enthalpy, what type of lattice enthalpy are we talking about here? So they have given standard lattice enthalpy of magnesium chloride and they have given a negative value. So if it is negative value, is it formation or dissociation? You have to think. If the lattice enthalpy is a negative value, now before you start the question, okay, if the lattice enthalpy is a negative value, is it formation or dissociation? Did you say dissociation? I heard dissociation as well as formation. So I'm just thinking what, now we'll take sodium chloride, Na plus gas plus Cl minus gas, right? We have NaCl solid. So if the delta HLE is a negative value, what is it? Formation. You need to give energy to break something. Think about that, right? Dissociation means breaking the lattice. So if you are giving some energy to break something, that is a dissociation. So if the delta H value is a positive value, that means we are talking about the dissociation. If it is a negative value, we are talking about the formation. So what enthalpy is given here in this particular question? A bit of an old question this is. So what enthalpy was given here? Formation enthalpy. That is formation enthalpy is given here, delta HLE. The standard enthalpy change of formation of H2O is given, and the standard enthalpy change of formation of nitrogen dioxide and enthalpy of formation of ammonia is given. Do this question. I will set the timer now. If you have any questions, ask me. You talk about ammonia. This.
In the fifth one, there is no charge.
You're asking fifth one, ammonia. Yeah, ammonia doesn't have a charge. Ammonium has NH4. This has a charge. Okay. See, they are checking your knowledge about enthalpies. So the first one is formation of nitric acid, the second one is magnesium chloride. I'm not going to discuss it now itself. After the time runs out, I'll do it. Right. Let's start. By now, you should be done. Are you done? Yeah? I gave you 8 minutes and I discussed a few of these as well. Now this actually, genuinely, 75 marks for this is such a waste. Such a simple question. Right? You should be able to get it done and save some time on this as well. But the thing is, sometimes as a cycle questions, they take a long time to write. Writing things and all that could be a bit problematic, but nothing more than that is there. So the first one, standard enthalpy of formation of hydrogen. So standard enthalpy of formation of nitric acid. So we can start with hydrogen gas, right, plus nitrogen gas, right, plus oxygen gas, and we form HNO3. Now according to the definition, right, HNO3, they are asking for formation of HNO3, we will say we are producing it as gas. Now according to the definition, students, we have to make sure, bear with me a second, HNO3 we will nitric acid, we get it as a liquid, right. So according to the definition, students, we are mainly focusing on the formation of 1 mole of product, and then we have to balance the equation in such a way that the coefficient here is 1. So that means you have half of this, half of, actually not half, 3/2 of this, and others we have to take half each. So we have 1 hydrogen atom, 1 nitrogen atom, and 3 oxygen atoms here forming HNO3. So that is the formation enthalpy of nitric. And then we have standard enthalpy change of magnesium chloride. So again this one is easy, magnesium solid plus chlorine gas. Now this is an easy mark because you don't have to solve anything. You turn into magnesium chloride solid, so it is automatically balanced, nothing to even worry about, right? So enthalpy, are they asking lattice enthalpy of magnesium chloride, not the formation enthalpy, sorry. So lattice enthalpy, what do you write for lattice enthalpy? Magnesium 2 plus gas and 2 Cl minus gas. Is that clear? So they are asking for the formation enthalpy by giving you delta H LE. They have given you value is minus 2500. So this is definitely formation enthalpy. You should write it this way. If it was dissociation, it was a positive value, that means you start with this and dissociate it. Clear? But it was a negative value, forming this formation enthalpy is given, that is formation enthalpy. Third one, the standard enthalpy of formation of H2O. Let me read it correctly. Formation, that means H2 gas plus, I will balance it directly and write, these are not difficult parts. So it forms 1 mole of H2O liquid. So you can even write the thing, delta H F naught is equal to minus 285 kilojoules per mole. And the fourth one, the standard enthalpy of formation of nitrogen dioxide. Again, formation, all the rest are all formations, that's why I thought initially this was also formation. So everything else is formation enthalpies. Nitrogen dioxide, you take nitrogen gas and oxygen gas turns into nitrogen dioxide gas, but you have to balance this. So when you're balancing it, you have to add a half in front, and we are, again, like I told you, we are trying to form only 1 mole of this. That means the coefficient should be 1. So when you're balancing, you add the you change the coefficient of the right hand side, left hand side reactants, not the product that is formed. So delta HF formation of nitric acid, nitrogen dioxide happens to be plus 33 kilojoules per mole. So this was an endothermic process, right? And last one is standard enthalpy of formation of ammonia gas. So then N2 gas plus hydrogen gas turns into ammonia gas, NH3 gas, and you have to have 3 of these, but since it's a molecule we have to divide by 2, and here we need to only have 1 nitrogen because we need the coefficient 1 here. Just to denote, we are forming 1 mole of ammonia. So therefore the delta H naught F value should be written here, minus 46 kilojoules per mole. Now this one I didn't write the enthalpy value, that is delta HF naught minus 207 kilojoules per mole. Right. So if you have written all of these, you get now 5 marks each. So 25 marks here. Normally you get 150 marks per essay. Actually, I was actually being too strict with you all. I forgot. Oh my goodness. These are essay questions, not structured essay. A structured essay question is 15 minutes. This is an essay question. So essay question gets 30 minutes. So half of an essay question would get 15 minutes. I'm sorry about that, students. Since it was, my paper, I have arranged it in this way. In my head, I was thinking, this is a structure. No, this is an essay question, right? 5 and 6, and even the 7th question has parts of physical chemistry. So 5th question usually definitely has an enthalpy part, right? So you can get up to 15 minutes, right? So sorry about that, but do you understand now, right? Then the second part, right? But I can justify it saying I'm teaching you to do it faster, right? So we move on to the second part. Have you all done the attempt the second part, right? But genuinely tell me, students, is this difficult? Right? This is not that difficult. This is around, I think, 2019. So this is not difficult. You can't tell me now 25 marks directly to you. The rest gets about another 50 marks for 75 marks, right? So I can't say even that is difficult. So using the above data, calculate the enthalpy change related to manufacturing nitric acid. Consider the following reaction set for it. So you can draw a HS cycle. Easy. If you haven't complete it now. I will give you 2 minutes. I will be writing this on my own as well. So you should be able to get to the answers within that time. Anyone? Sorry. Can I erase the top bits? Right. I will rewrite this part. Everyone done taking this down? See whether you can get to the answer. Now they are saying starting with ammonia, then reacting with oxygen to form nitrogen monoxide, and nitrogen monoxide reacts with oxygen to form nitrogen dioxide. That form nitrogen dioxide reacts with water to form HNO3. Right, so now students, I have given you few steps. Now the reason why I wrote it like this is to show you what we are doing here. So the three equations are given here in this paper. So we can see ammonia reacting with 5 water molecules, so 5 oxygens form 4 nitrogen monoxide and 6 water molecules. So the number of hydrogen, oxygen, everything here is perfectly balanced. Now if you take a look at this one, imagine right after this we take this particular step. Do you see the way that I have written it? The NO over here and NO over here, they get the whatever the NO that is used made up here gets used up here, right? And then for that we need 2 more oxygens, and you form finally this. And afterwards, whatever that is formed here, nitrogen dioxide, is used up here. So we can actually cancel them off. Okay? And when you do that, we get to one equation here. And keep in mind, students, now we have to balance this. Now this is currently not properly balanced. So we have 4 hydrogens, no problem. We have 4 nitrogen and 4 nitrogens, 8 oxygens, and actually, yeah, oxygens are properly balanced. It is clearly balanced. So we have 10, 12, all of the equations are balanced here. Now when you are adding them up, then the things that are on both sides usually get cancelled off. So we can see NO got cancelled off to NO here, NO2 got cancelled off to the total number of NO2 here. Apart from that, is there anything else that we can cancel off? We'll see. So first of all, we had whatever that is on this side. We have 4 NH3 ammonia gas, and then we have 5 oxygens, 7 and 8, let's say plus 8 O2, turns into HNO3, 4 of them. And apart from that, we have to see whether we can cancel anything else off. Yes, we can. We have water here, water on the left hand side, water on the right hand side. So there are 6 of them. Out of that, 2 of them is used up, so that means you have 4H2 remaining here. So on this side we can add 4H2. Now do you see everything here is divisible by 4? We can simplify it and write NH3 gas plus 2O2 gas turns into HNO3 liquid plus H2O liquid. Now from here onwards, it's a simple formation enthalpy. We need nitrogen gas, we need oxygen gas, right? We need half a nitrogen gas actually, and we need oxygen gas, we need hydrogen, right? 3/2 hydrogen gas. Now these can be used to form ammonia. Oxygen, does it have to be formed? Oxygen in its element form, does it have to be formed? No, there's no formation enthalpy for standard state elements. Nitric and H2O should be formed. So this is the reaction enthalpy, delta H R. Now this is our delta H formation of NH3 gas. This is delta H formation of HNO3, and finally you have the formation of H2O. Right? I will write the Hazer cycle here. Write the Hazer cycle here. Right, so delta H formation of ammonia plus delta HR is equal to delta H formation of a nitric plus H2O, formation of H2O. Bear with me. So ammonia formation enthalpy is given here, minus 46 kilojoules per mole. You have to substitute with the correct unit, but I don't have the space here, so I'll for the time being leave it like this. And formation enthalpy of nitric is minus 207 plus H2O. H2O is minus 285, right? So the only thing that should be multiplied if it was formed was oxygen. There's not formation of oxygen, so therefore we don't have to multiply anything. Everything is just this. So that means delta HR is equal to, let me do the math here quickly, 207 and 285. Now this side is minus 492, and this minus side, minus 46 goes to the other side, it becomes plus 46. So it becomes minus 446 kilojoules per mole. Is that clear?
Sir, because he has plotted us all the formation enthalpy, can we just use the last equation and you draw a Hess cycle to it?
Now you're asking whether we can use this particular equation
And draw a Hess cycle.
because you know the formation of this and that, right? You can do it, you can find the formation enthalpy, but then again they will not give you marks for it. The reason is, they say, using the above data, calculate the enthalpy changes related to manufacturing of nitric acid. Consider the following reaction set for it. Do you understand? So they, like, you can definitely, but the thing is, theoretically what you're saying is true. If you know the like formation enthalpy of this, formation enthalpy of this, and formation enthalpy of this, you can calculate the manufacture the reaction enthalpy for just this. But the manufacturing process includes all these three steps. Do you understand? Now for the last one you can find the reaction enthalpy for sure, no problem that way. But they are saying manufacturing process is this, these are the reactions. Consider the following reaction set for it, they have mentioned, right? So then you will not be given marks for that part. Okay, good question. Even initially when I read the question incorrectly, that would have been my assumption as well. But in this case, since they are specifically asked you to consider these, we have to consider them. Now the whole cancelling off of things, don't worry, okay? You will be learning about these things in another part, especially when it comes to rate. You will be learning about different types of reactions. Now I will, while you take it down, I will brief you on that as well. There are certain chemical reactions that happens in a single step, right? Those are called elementary reactions. And there are other steps, other reactions called complex reactions that take place in few different steps, right? So in that case, just like here, this is actually a set of reactions, not a single reaction. Set of reactions, you can see one thing that gets formed here gets used up in another step, and again one of the products that gets formed here gets used up in another step. So there we learn how to nicely cancel these things off, like just like we have done here. Now you have learned about it, right? So then after doing that, you get the full equation by adding everything that is remaining. Clear? So then you get to this. Is it understood? Right? So although you come across this now itself, keep in mind you will be comfortable with cancelling things off, finding out connections like this in the future as well. But right now, since we learned this, I want you to be okay with this part, right? So basic theory that revolves around this cancelling off parts is given to you here. Right, shall we take a small break then? After that. Now since it's like a 4-hour class, we'll take a break till 5:20, half an hour break, right?
Sir, in that case, now they are using the manufacturing process. In that case,
So since I got about 5 minutes late, did any of you attempt the 5th question? None of you attempted anything all this time? Right. So what do you think I was going to do after I came? I was going to ask you to do the 5th question. Do the 5th question. In the sense, the next question, the reaction X Y2Z2 gas breaks into this. In A, Gibbs free energy G at 250 Kelvin for this particular reaction are minus 60 kilojoules per mole, 76 kilojoules per mole and 30 kilojoules per mole respectively. So they have given the 3 reactions and then they are asking you to find out the answer that is given here. Try to do this question. Now Gibbs free energy is also something like what? Is also just like enthalpy change. So can you remember, like, delta H is equal to the enthalpy change of so enthalpies of products minus enthalpies of reactants. Can you remember that? So similar approach can be taken here to calculate the answer to this question. Okay, attempt this question please. So I'll give you 10 minutes or maybe 15 minutes for this one. This is a bit difficult. Anyone who's done? Who is done? Fifth one, last one. Okay, we'll get to that. So for the first one, did you get to this answer? Everyone? This is simple one. For the second one, did you get to this one? So what did we do here? Now we'll discuss the question, okay? So we have, when it comes to Gibbs free energy, that is also something similar to delta H, right? We can think of a quantity like, that has parallel properties, that is delta H. So usually we can use the same equation. Delta H is equal to enthalpy of products minus enthalpy of reactants. Delta S is also equal to entropy of products minus entropy of reactants. Delta G is also equal to entropy of products minus entropy of reactants. Sorry, Gibbs free energy of products minus Gibbs free energy of reactants is equal to delta G. Is that clear? So we can easily get to this answer. The second question says, the magnitude of delta S of the above reaction is 150 joules per Kelvin per mole at 480 Kelvin. Calculate the delta H for the reaction at 480 Kelvin by using the appropriate sign plus or minus for delta S. Now they are not directly telling you whether the entropy value is plus or minus, but I have used plus here. Can someone tell me why that is? I am assuming entropy is increasing. Now why do I assume entropy is increasing here? I told you now, there were three main things I told you last week about entropy change. What is it? If a solid turns into gas or a solid turns into liquid, that means entropy is increasing. If a liquid turns into gas, entropy is increasing. When you're going from solid, liquid, gas, entropy is increasing in that order. Now there's nothing like that happening here. What is the other thing that I mentioned to you?
The amount of things increases.
Yes, exactly. If the number of reactant particles, and when you're comparing number of product particles, as the reaction happens, if the product particles increase, then what happens? Entropy increases. When something breaks into two, there are two things now. Entropy increases. The more particles you have, the greater the increase in entropy. Clear? So here we have one gas molecule turning into two gas molecules. Entropy is for sure increasing. Is that clear?
So, but why didn't you put G value positive? They calculated G is
Right. Yes. Yes. Exactly. Sorry. Then there would be a small issue here. That was a mistake. Right? That was a mistake. G should be negative. Right? G should be negative. So we'll quickly. And why did I write the G value here as 46,000 joules per mole?
to balance the signs.
To make sure, yes, the units are the same. Right? To make sure units are the same. So at that point, students, we have here, when you are sending this thing to the other side, we have minus 46,000, and this is going to be now when you are bringing minus 46,000 and then this to the other side, this will be positive. What was the value you got here? 72,000. Right? So then the difference between the two should be written. So you have 6 here, 26,000. Yeah, so 26 kilojoules per mole, and this is going to be positive, right? So 72,000 is greater than 46,000, right? So this is joules per mole, this is kilojoules per mole, right? So this is the answer for that question. So now they're asking you, based on that, they can also ask you whether this reaction is spontaneous. What do you say? Delta G being positive means what? So earlier here itself we could have answered. Delta G was negative. What does that mean? Delta G being negative means what? Spontaneous or non-spontaneous? spontaneous. And although it was spontaneous, we can see the enthalpy value was endothermic. You see, endothermic reaction can be spontaneous. We know a few endothermic reactions that are spontaneous anyway. Like when dissolving glucose in water, it's a slightly endothermic reaction, but still it takes place. Then they ask you by using the sign of signs minus or plus of delta H obtained, explain whether this reaction is exothermic or endothermic. Deduce the enthalpy difference for the formation of this particular gaseous compound and XY2 and Z at 480 Kelvin. Deduce the enthalpy difference for the formation of this particular substance. Did you do that? So what is enthalpy difference? Minus 26 kilojoules. Correct. So because if you are talking about this reaction between, if you go basically, how do you calculate the enthalpy change? Delta H is equal to delta H higher enthalpy of products minus enthalpy of reactants. So that value is given here, but the opposite of this should be taken. Clear? Deduce the enthalpy difference for the formation. So those of you who are still wondering what that is, now the equation that is given to you is this: x y to the power 2 z to the power 2 turning into x y2 plus z2. Basically this is a dissociation of that compound. So this has a delta H value that is positive. So formation would be the opposite of this. However, it will be the same magnitude. Whatever the X value should be the same value here. Enthalpy values will not be different. However, since it is going in the other direction, the sign will be negative. Is that clear? We learnt about this in thermochemical equation part in the lesson. Now the fifth one is not that difficult, students, if you know bond enthalpy related knowledge. If the bond enthalpy of XZ bond in XY2Z2 gas is plus 250 kilojoules, calculate the bond enthalpy of ZZ bond. Calculate the bond enthalpy of ZZ bond. Now, anyone who did that? So, you draw a graph, you draw a Hazer cycle. You can do that. Or you don't have to, draw a Hazer cycle if you feel like you can directly get to the answer, because we anyway know the equation. Now, I will guide you to this. Anyone who actually got to the answer? No? None of you? Right. So, we will see. We have this equation. I will write the compounds with the bonds itself so that it will be clear to you. This compound breaks down to X Y2. Right? We'll say and Z2. Now they are giving you the bond enthalpy of breaking off XZ bond. That means this particular bond enthalpy now that means, anyway, we already know that the total enthalpy change of this reaction. What is that? Also, I'll write that here. Delta H reaction enthalpy is how much? It was plus 26 kilojoules per mole, right? That's what we obtained, right, earlier? So then, try to find the rest of the equation. Try to draw a Hazer cycle and see. Now, if you feel like there's a piece of information missing, let me know. There might be there's one bond that seems to be giving a bit of a problem, but still try to find the answer. Actually, my bad, this was given as X, Y2. I'm not going to reveal the answer there, just leave it be this way. You are going to be able to calculate this for sure. You don't have to draw a Hess's cycle if you don't want to. You can use a basic equation that we have told you about earlier. I will give you a refinement to that equation as well, but for the time being, try to use your common sense and get to the answer. Now they have given you only a limited amount of information. One is this bond, and they are asking for this bond. Now I told you, I'll give you only this much of information. I told you, when a chemical reaction is happening, to break bonds, we absorb energy. And when bonds are formed, we release energy. Clear? Now based on that, try to get to the answer. Now I will tell you one thing, the answer might be more closer than you think. You don't have to do very difficult calculations here. It's a thinking question. Now if I'm being even more giving you even like a bit of further assistance, take a look at now what this structure looks like, and then take a look at what the products are. And to form the products, you need to break some bonds here and form some bonds there. Do we break all the bonds? That is a question you have to ask, right? Then answer. If you got my hint, you should be able to answer. Do we have to break all the bonds to form the products? Anyone with the answer? Joules, no? Wait, you don't want me to tell you? No. That?
No, I think I got this. I need to think.
Okay. So think logically, students. Don't draw Hess's cycle. Think logically. Now, let me explain this to you. Right. So we learned about this equation. Can you remember? Can you remember this? Right. And there is an alternative form of that equation, that is this. Bonds broken minus bonds formed is also equal to reaction enthalpy. Either one of these can be used to answer the question. Now this one can easily be used, but even this is possible to be used. So your understanding lies here. Now they don't give you the structure of all the compounds. That is done intentionally to make you think. So now they are only saying this bond enthalpy is given to you. Why in the world do they do that? Because they want you to think. If those bonds are broken, what is it that is formed? XY2. So that's why I didn't properly give this one's formula or bond structure earlier. Because if that has been given, there's nothing to think about, then the answer is very clear. So when this is broken, you form XY2. So basically, students, here the structure is this: X, Y and Y. So earlier we had this. Now imagine we are using that equation. Delta HR is equal to reactant bonds that are being broken. So we can write there are two ZX bonds plus there is two XY bonds. Now from this we have to subtract. I will erase this part. From this we have to subtract. Now these are the reactant bonds minus product bonds. Now product bonds are again 2 delta HD X Y plus we have delta HD Z Z. Now when you open brackets, you can very clearly see these two anyway cancels off. Now this one we already know, this is 2 into 250, but we can say this is plus this bond value and this is minus this bond value, plus that bond value minus that bond value. Basically these two cancel off, isn't it? So then we have only this one, that is going to be minus delta HD ZZ equals to plus 26 kilojoules per mole. So then we take it over here, 26 goes there, so delta HD ZZ is equal to 500 minus 26, which is 474 kilojoules per mole. Understood? Or you can use this equation. Now that equation is another easier alternative form. In that equation we are only looking to break or form the necessary bonds only. The unnecessary ones we don't even touch. For example, here if you break these two bonds, anyway we are getting this. So is there a point breaking these two bonds? No, right? Imagine you are trying to make something new. Imagine you have a Lego set. Now you have made something like this, but one of the things that you want to make after breaking this is this. So do you have to break this apart again into completely like tiny pieces? No, you can keep it and just remove this one, right, and then leave it in a separate place. Do you understand? It's like this here, and then here we have this, we have this. Do you understand? So in order to turn this thing into the products that we have over here, we have to first break these two bonds. So the bonds that are broken are taken into consideration. So only bonds broken will be mentioned here, and then minus the values of the bonds that are formed, right? So basically you get to this. This part is basically representing bonds broken, and the minus this part represents bonds formed. Is that understood? Clear? So then you anyway get into the same answer, plus 474 kilojoules per mole, and it should be a positive value. Why? Because we are talking about dissociation enthalpy. Dissociation enthalpies are always endothermic. Clear? Do you understand now? Take it down. You can actually, after taking it down, maybe rewrite another equation with this, just to get it clear to your heads. If a liquid is used instead of gaseous, given reactions with the value. obtained. Right, the last question then. Bear with me. Right, they say if liquid XY2Z2 is used instead of gaseous XY2Z2, giving reasons, explain whether the value of delta H obtained for the reaction is equal to or higher or lower than delta H obtained. Now this is a classic example of what I just said when it comes to talking about the previous equation. Can you remember when I gave you that equation? I said sometimes some people use this to calculate reaction enthalpy even when this is a liquid, right? I told you there is a bit of a problem with that, right? But still sometimes some people do it, I told you, right? That's wrong. So why is it wrong? Because when you have a liquid here, now bond enthalpies are defined as what? The amount of energy needed to make 1 mole of bonds when the bond is present in gaseous state. If it is present in liquid state, can we talk about a dissociation enthalpy? No. Now this is in a liquid state. So if that is the case, we have to first turn it into a gas. Is it an exothermic process or endothermic process? Endothermic process. So that means the liquid should be first turned into a gas, energy absorbing process. So therefore what happens, students? More and more energy has been absorbed. This process was anyway positive in enthalpy change, right? That means what? This process was endothermic, and add to that the liquid turning into gas is also endothermic. So then what happens to the enthalpy value? Increases. Clear? From plus 26 it could go to about some other positive higher value. Is that clear? Right. So the answer should be the enthalpy value is positive and liquid turning into a gas is also a positive enthalpy value. Therefore there will be an overall increase of enthalpy. There will be an overall increase of enthalpy. Or you can just say this previous reaction was endothermic and the liquid turning into a gas is also an endothermic process. So therefore the overall enthalpy value will be a greater positive value, or it will be increasing. I want to do a Gibbs free energy part, include one as well. Don't worry about the next question, the fifth one in the next page. We don't have to do that. You can do it at home. There's a B part that is still not something that you can do, but I included it because the A and the C parts are things that you can do. You can do it at home. Do the third question. There's a question number 3 here. There's a question number 3 here with a diagram. This is a structured question. This is a structured question. Attempt that question, please. Have we done? Done? Anyone who's not done yet? Everyone is done? What is the difficult part here? Is there a difficult part here? I'll give you 2 minutes. Is this correct? Did you get to the answers? Shall we discuss now? I think it's somewhat enough time now, right? Shall we do it now? Right. So let's explore what is going on here. They are saying 0.1 moles of a solid called Mx is dissolved in 100 grams of water, or 100 cubic centimeters of water, which is 100 grams of water. Then the initial temperature was 25. After dissolving it, temperature decreased to 17 degrees Celsius. So 8 degrees Celsius difference. Now at that point, we have formed a solution with what? 100 cubic centimeters of water and 0.1 mx. Now students, they are asking you, the first question is, what must be the energy provided to bring the solution all the way back up to 17 degrees Celsius. 17 degrees Celsius. So that means when you use this, you have to keep in mind, now we are at 17, we are bringing it up to 25. So the temperature difference is a positive one. Clear? Right? So you are going to this answer. Now even if you don't think of that and get to a negative answer, but you still find it right, this much of energy should be supplied. That gets the point across. Clear? But understand what they are asking. You are at 17, you have to bring it back to 25. Now the second question is the dissolution of Mx in water endothermic or exothermic process? Now they are trying to trick you with this, right? So this was a positive one, and now you would usually calculate the other way around, and you know, okay, if the enthalpy change was negative, then that means the process was doing this. Now they have asked you a different question, and now they are asking whether this is exothermic or endothermic. The simplest answer is this is a endothermic reaction. The only explanation you need to give is the temperature decrease. Now I have given you a bit of an elaborate one, but if you said temperature decrease, that is enough. Temperature of what decrease should be mentioned? Temperature of the solution, or temperature of the medium, temperature of water. That is okay, right? Temperature of water decrease. Why? Because as the reaction took place, that process absorbed energy from the water. So should be the temperature of the medium decreased as the dissolution of the solid absorbed energy from the medium. Is that clear? Right? So this is endothermic for sure. And then the third one, calculate the enthalpy change in kilojoules per mole associated with this reaction. So basically what we have found out when we are dissolving this, so that is dissolution enthalpy that they are asking for. So dissolution of 0.1 of the Mx solid absorbs this much of kilojoules of energy, right? It's an endothermic process. So if this much absorbs this amount of kilojoules, if we dissolved 1 mole of this substance, it would absorb 3.6 kilojoules, 3.36 kilojoules divided by 0.1, so which is 33.6 kilojoules per mole. Is it understood? So whenever you are talking about enthalpy change, you can't keep the final value in just kilojoules. That means you have to calculate how many moles release this. Okay, 0.1 moles dissolving in water release this. That means, not release actually, absorb this. That means if you take a look at 1 mole of substance, when that dissolves in water, this much of kilojoules per mole will be absorbed. So that is the dissolution enthalpy of Mx. Is that clear? And it should be positive. Why? Again, the temperature was a decrease. That means the process was endothermic. Is that understood? Right? That should be clear to you. Now, fourth one, again theory part. If this experiment was conducted using 200 cubic centimeters of water, would you expect the temperature change to be larger than the above value? Explain your answer. Now you answered that earlier. What is the answer? Will it be greater or decrease? Will it be greater or decrease? Read the question again. if the experiment is conducted in 200 cubic centimeters of water, would you expect the temperature change to be larger than the above value? Explain your answer.
Same.
Right. So, what is the question? Why do you say it's the same? It's not the same, no? Why is it the same? Why do you get to the wrong answer here? So, read again. If this experiment was conducted 200 cubic centimeters. Now, how many cubic centimeters do we have? 100. Imagine they say if it was brought to 200 cubic centimeters and you are doing the same thing, meaning you are taking 200 and adding 0.1. Right, don't go further away from the answer. Right, so first of all, take a look at this question. So the answer here. So, did we increase the number of mx? No. So this amount of mx, when dissolves in water, it absorbs this much of kilojoules of energy. So what does that mean? Does the Q change? Does the Q change? No. Does the M change? Yes. So basically if M increases while this is still the same, C is not something that is going to change, right? That means T should be decreasing. Right? Do you understand? Now for example, if I ask you this question, you have an electric kettle, right? When you put a little bit of water and then put it on the heater, it will heat fast. Same amount of heat is given per second, but it will heat fast. Why? The amount of water that is there to absorb the heat is less. Clear? But if you put about 1 liter of water, it takes about 30-40 seconds. Why? Because it gives heat off in the same rate, the heater. But there is a lot of water to absorb it, right? So do you understand? So means what? When there is a lot of water, there's more water to be more water there to absorb energy from. So the overall temperature decrease is less. Is that clear? Now, water is a good heat, good coolant. The more you have of it, the more the cooling effect. So when there is a lot of water, when a chemical reaction is endothermic, it will provide more energy to that substance. So basically if you have more water, the temperature decrease in the water is less. If you have only a little bit of water, it will be greater. You can understand it through this equation. If the Q remains the same because we didn't change this. If we change the amount of mx, if we increase it to let's say 0.2, then Q will also change. Now Q didn't change here. Mass changed, so therefore T has to change, delta G has to change. Understood? Got that one? Right? So therefore students, the answer here is, they're asking you whether it will be larger. The answer is no. Explanation: there is more water here, therefore the temperature decrease will be smaller. That is sufficient. More water, temperature decrease will be smaller. You don't need to explain all this equations and all that. We can write this: there's more water to give off heat. Can I erase some of this now? Right. Okay, this is a good one. Show the variation of temperature of the system, or which is a solution, by drawing the temperature time curve. Eventually the system reaches room temperature, so you have to show that as well. Eventually it reaches room temperature, you have to show that. So we have the temperature axis here and we have the time axis here. This is temperature. We'll say they are talking about temperature in Celsius, right? So we'll talk about Celsius here. Time, let's say seconds. Now we are starting at 25 degrees Celsius. How did you draw it? Anyone drew something like this? Seems to be what is happening. Right. You decrease the temperature, it increases back. Is this correct? Does it decrease this way though? No, students. Usually the decrease will be bit of a curve. Temperature won't drastically go down like this, like in a straight line. Usually it decreases like so. Right, we get to a simplest value, the smallest or minimal value here, right? And then now we're talking about as the reaction happens, the endothermic reaction, so the temperature decreases, and then it comes back up to 25 degrees Celsius. Can I know how you drew this? Did you draw something like this? Something like this? Bear with me. Coming back to 25 again. Did you draw something like this? No? What did you draw then? Similar. So now we usually like this kind of symmetrical ones. Some of you would have drawn this. That's why I gave you.
Second part, gradient should be lower than the first case.
Exactly. That is what you should think. Right? Now this temperature decrease was forced by a chemical reaction that was happening. So basically the temperature decrease, the chemical reaction don't take ages to happen, or it happens a bit fast, a process. So basically the temperature dip was somewhat fast. But then temperature increase can't be as fast as that, because it is absorbing energy from the surrounding and increasing in temperature. Nobody is heating it up. If someone was heating it up, it could be like drastic like this. Nobody is heating it up. It absorbs energy from the surrounding. Nobody is forcing it to absorb energy. But due to the temperature difference between the environment and the system, slightly there is a energy intake from the system. So that energy absorption leads to a temperature increase very gradually. So like this. So the gradient here should be greater than the gradient here. Clear? Because this is a forced thing, and this happens naturally. Right? So usually those things are somewhat slow. And this we did quickly. But this temperature increase will happen gradually. Is it understood? So that is the curve. Now these are things you have to think and do.
Can we add the 17 Celsius to the bottom?
Yeah. You mean here? Yes. You have to. Right? But the curve shape is also quite important. Clear now? Good. So now explain why the plastic cup is used instead of a metal cup. What is the reason? Plastic cup is a good insulator, right? Metal cup is a good conductor. So that makes sense. We want to make sure the energy is not escaping the system. So to insulate, we use a plastic cup. But the answer that is given here is metal is a conductor, right? But it should be a little bit more elaborate than that. Clear? Now Gibbs energy change delta G for the dissolution of MX in water at temperature of 25 degrees Celsius and pressure of 180 m was calculated to be minus 26 kilojoules per mole. Calculate the entropy change of dissolution of MX. Entropy change of dissolution of MX in water at 25 degrees Celsius using enthalpy change calculated above. So yeah, that is quite easy. Did anyone calculate the entropy change? Can I erase this? Can I erase this? So delta G, now this equation I'll have to keep it in the board for the next one as well. delta G is equal to delta H minus T delta S. Delta G, they say, was 26 kilojoules per mole minus 26.0 kilojoules per mole. Now shall we keep everything in kilojoules per mole this time? It will be easier that way. But we are asked to calculate delta S. So we'll convert everything into joules per mole. So we have 26,000 joules per mole here, and delta H, what was the delta H we calculated? 33.6, right? So that means this was plus 33,600 joules per mole. That was endothermic process. And then minus 25 degrees Celsius means 298 Kelvin. This has to be always in Kelvin, and we are trying to find out delta S. We don't know that, right? So when you try to bring this delta S over here and then send this over to the other side, now this was minus, right? So then we have 298 delta S is equal to 33,600 minus, actually when you bring this to the other side it will be plus 26,000 joules per mole. So this becomes 59,000 joules per mole, 59,600 joules per mole is equal to 298 delta S. So to get to the answer we have to divide this by 298. So we can see this nicely cancels off, leaving behind 2. Right, so this is delta S happens to be how much? 200 joules per mole. Actually I missed a Kelvin sign here, so that this unit is Kelvin. So joules per Kelvin per mole. Kelvin is there, right? The unit shouldn't be missed. Joules per Kelvin per mole is the unit for delta S. Clear? Okay, so now after doing this they are asking you another question. Now entropy is increasing, students. Usually dissolution usually increases entropy, right? You have a solid which is tightly packed, and then you have a solvent which has molecules that are freely moving. But when it is dissolved, we have a solution where we have molecules that are freely moving of the solvent. Apart from that, we have solid molecules also, or solid particles also, now freely moving. Entropy has increased. Earlier solid particles were in a well organized manner. Usually, not all the time though, usually it is increasing in entropy. Clear? In general. So this proves that this is delta, so delta S is positive, right? Now the next option, next question, they are asking you, would you expect the solubility of Mx to increase or decrease with increasing temperature? Give your reasons for your answer. What is the answer that you gave? Solubility increases or decreases? Sorry? Increases? Decreases? Why decreasing? So now students, delta G should be looked at. Delta G equals delta H minus T delta S. Now make note of these things. If delta G is negative, that means what? Spontaneous. The greater the negative side, the better, right? That means it easily dissolves or easily spontaneous. Clear? Now these values, delta H and delta S values, we usually think with temperature they don't significantly change. Delta S usually changes, but in this particular scenario we can assume, sorry, not delta S, my bad, right? Delta H usually don't change with temperature that much. There's no significant increase in delta H with temperature. But if you take this term as a whole, and we know delta S increases the temperature, delta S usually increases the temperature, but if you take this entire term as a whole, as temperature increases, this entire value increases, right? And that entire value is a negative value. Now the delta H for this particular question was a positive value. Is that clear? Now imagine, for this to be a large negative value, we have to have this negative value over here increasing, isn't it? So when the overall negative value in the equation is increasing on this side, as a result the delta G value increases. Is that understood? So as the temperature increases, this entire negative value, because this is negative and delta S was positive. If delta S was negative, you have a problem. Why? Because this is negative. Now imagine negative, you have a temperature value multiplied by another negative delta S value. So negative will be positive. So then we have a problem. In this case we don't have that problem. We have delta S as a positive value. So when delta S multiplied by a higher temperature, the resultant value is a greater negative value, right? Then what happens? Since this pretty much remains a constant, delta H doesn't change, this remains a constant, so therefore this will increase. Is that clear? So delta H, students, ever so slightly changes when temperature increases, but that change is considered to be not that important. Clear? So you can write down, you can actually write down that and then write as temperature increases, minus T delta S value becomes a larger negative value. Which makes delta G a larger negative value, which indicates process is more feasible. Solubility increases. Is that understood now? Clear? So students, you can do, there is about another one question there. Actually 2 questions we couldn't do them at home. Shall we attempt some MCQs? Right? I want to attempt some Gibbs-free energy related MCQs, because enthalpy is like, we have a lot of enthalpy related questions. Turn to Gibbs-free energy related MCQ part. I want you to pay attention to these type of ones. So attempt question number 6 and 8. 6, 8, 11. We'll do 3 questions. We'll have time. 6, 8, 11, 13. 6, 8, 11 and 13. Do these 3 questions. Actually 4 questions. under Gibbs free energy. So here, under this relationship between entropy and Gibbs free energy, under that topic, do question number 6, question number 8, question number 11 and question number 13. Some of these questions like about equilibrium and all that you can't still do, but have it, because by the time you can do it, when you're doing this tute again, you'll be able to attempt those questions as well. So the 11th one, take that the entropy change of the at the two temperatures is not changing. Okay? Then at that point you can calculate the entropy change. Are we done with the fourth question? Or fourth in the sense the 13th question. Shall we discuss? Right? So this Gibbs free energy questions are important because enthalpy is quite mainstream. You have a lot of questions that you can do. So some students, they give out on entropy and Gibbs free energy. So we'll focus on these a little bit, right? Now let's take a look at these questions. Question number, I said start with question number 6. What is the answer for question number 6? 1, 2, question number 6, right? 3, 4, 5. What about the girls? What is the answer? Let's see. When solid ammonium chloride dissolves, temperature in the solution decreases. Which of the following is true about delta H and delta S? Now students, if the temperature is decreasing, if the process is endothermic or exothermic? If the temperature of the medium decreases, the process is endothermic, right? If something is giving off heat, then the temperature of the medium increases. If something is absorbing heat, then the temperature of the medium decreases. So the process is definitely endothermic. So this has to be positive in delta H value. Which of the following is true about delta S though? So delta S, right? Now answer to that is this: delta G equals delta H minus T delta S. Now if delta H is already a positive value and delta S happens to be a negative value, then negative will become what? Positive. So that means delta J is positive. When delta J is positive, the reaction won't be spontaneous, right? So that means this cannot be negative. If this was negative, this is not taking place. Is that clear? So therefore students, this has to be positive, then this is going to be negative. So if this value is a greater negative value, at that point this is going to be negative. Clear? So what is the answer? Delta S is a positive value. Clear? You use this equation, that's it. Use logic. So the answer to that question is positive. First one, delta H is positive, and then delta S is also positive. The 8th question. A reaction is spontaneous at 298 Kelvin and 100 kilopascals pressure. While it is non-spontaneous at higher temperatures and the same pressure, which of the following is true for this reaction at 298 Kelvin and pressure? So 298 Kelvin and 100 kilopascal pressure, it is spontaneous. But higher temperatures, not spontaneous. What could be the reason? What could be the reason? That means,
S is negative.
yes, S could be negative. So students, if this is higher, now we'll take this example. We have to have this negative. Now imagine if this was positive and this happens to be also positive, the final answer is, like, when you multiply this with T, when T increases, the entire negative term increases in negative value. that means it's good. It is going to be making it a larger positive value. So definitely this is not positive and this is not negative. Clear? So let's switch it. Let's see if this is negative and if delta S value is a positive value, what happens? Imagine now we have minus positive value. Then if delta T increases, it's a good thing. This entire negative term, now negative positive will add up to be negative and it increases in negative value. This is also negative. So good. What happens? This increases in negative value. Means it is going to be possible at higher temperatures and much like it is going to be more feasible at higher temperatures. But that is also not our option. That means you can actually develop an idea. So you can develop the idea when temperature increases, if the reaction is not going to be feasible, that means this is going to be positive or more positive as the reaction increases in temperature, right? And this has to be negative. So you can immediately think that also, because temperature increasing would increase the magnitude of this value, and if the magnitude happens to be a positive value, the overall magnitude, imagine overall magnitude happens to be a positive value, then it's not going to be good for the Gibbs free energy change. So imagine if this was negative, then the overall value is positive. Clear? If delta S is negative, this overall delta S multiplied by T and there's a minus sign here, this entire term is going to be a large positive value at a higher temperature. So this is going to be large now, while this remains the same. So then the overall value is going to be a large positive value. Is that understood? So therefore students, you have to choose the correct answer here. Delta H is negative and delta S is also negative. So negative and delta G also should be negative at 298 Kelvin. So the answer with all negatives is 2. Answer is 2. Right. 11th question. We'll finish off quickly. 11th question. Anyone did the question? To be honest, students, like the 11th question and all that, there is no such theory part that we use to teach you this. This is basic exam practice, being battle ready. They don't say okay, go do this. You instinctively know if someone comes at you, do something, right? Just like that, nobody teaches you okay, when it comes to a question like this, answer this particular way. You do the math there. So what is it that you can do here? You know the temperature, you know the Gibbs free energy, you don't know delta H, you don't know delta S. So you write this equation. You can write two expressions. You can do the math here in your head, to be honest, but we'll write it. Right, delta H minus T delta S. Right, for the reaction number 1, delta G was minus 100.2 kilojoules per mole. So this is kilojoules, we'll write it as joules per mole by multiplying with 1000. Delta H we don't know. Temperature is 1000. Do we know delta S? No, we don't. So this is expression number 1. And then we have expression number 2. That is minus 148.6 into 10 to the power 3. Delta H doesn't change, it's the same. And this is 2000 delta S. We are, in this case, the entropy change we have taken as something that doesn't change. Entropy changes, so let me rephrase. The concept of entropy increases the temperature, but they have taken here entropy change has not increased. You understand? Reactance entropies as well as production entropies has increased, but the gap between them has not increased. Clear? So now we can just write 1 minus 2 or 2 minus 1, whatever you want, but I will go with 2 minus 1. So we have minus 148.6 plus 100.2. I'm going to directly write the answers, like you are not babies, you can actually understood what has happened here, right? Hopefully, right? This is equal to, again, I'm not going to babify you, delta H cancels off. So therefore we have minus 200 delta S. I can take the delta S part out actually. Minus 200 plus 100. Actually 2000 plus 1000 delta S. So the answer that you get here is minus 48.4 into 10 to the power 3, and over here you get to minus 1000 delta S. So you can see this cancels this off, minus cancels off, it will be 48.4 joules per Kelvin per mole. Delta S is equal to 48.4 joules per Kelvin per mole. Here they have 48.8. I think it's a typo from my typist. So it is 48.4. The third answer would be the answer.
So we can add those equations and find.
Yeah, you can actually do that also. What did you do?
I subject the S and I subject the S in those equations and I add those and I found the 8. Then I substitute the H with the equation. Then
Okay, you can do that also. But then again, do you understand, like it's a bit of a lengthy. So since they are not asking for this, we can get away with not finding delta H. Clear? Because when you do it that way, you are cancelling S's off, right? So you can actually do it this way, right? So now last one, enthalpy change of vaporization and the entropy change of vaporization of a liquid are given to you. Entropy and enthalpy are both given. Calculate the boiling point of the liquid. Calculate the boiling point of the liquid. Now students, will water boil at 95 degrees Celsius? No. What do you think the delta G value of that process is at 95 degrees Celsius? Water turning into steam. What is the delta G at 95 degrees Celsius? Do you think it's a positive value or negative value? Negative value, right? What about 101 degrees Celsius? What is the delta G for boiling water? Positive value, because in that temperature water only turns into steam. But I have told you many times, at 100 degrees Celsius or at a boiling temperature of a liquid, we have both of these happening. H2O gas as well as H2O liquid. Can you remember I explained this in gaseous systems? Any liquid has a vapor phase. Told you this, right? So when it comes to boiling temperature, what happens is this equilibrium is existent, and from beyond that temperature it only goes towards steam. Clear? Water starts to boil at 100, and until actually you can't, like without pressurizing it, you can't turn it into a higher temperature, but at this temperature only the water starts to boil. So what is the delta G value at that temperature? What should be the delta G value? 0. We usually, whenever we have to find a temperature value for a chemical reaction, if they ask you find the temperature at which this reaction becomes feasible, we always take delta G 0. Clear? Delta G should be minus values, but we can't take -1 and do the calculations. So we write delta G is 0 and do the calculation. So then when we do the calculation based on that, if I write the values, just 2 minutes, sorry about this, we have to do this calculation and finish it off. So if this is 0, vaporization enthalpy is 45,000 joules per mole, and the other one is T multiplied by 90 joules per Kelvin per mole. So this is 0. So you bring it over here. So T, 90 T is equal to 45,000. So it's going to be T equals 500 Kelvin. Okay, simple. Normally they give you very simple answers. So do we have the 500 Kelvin here? So we don't have 500 Kelvin. What is the answer? 227 degrees Celsius. Students, please do the Gibbs free parts, because I feel like that is a bit important. Enthalpy parts are also very important. That's like the mainstream one, but like, you know, Gibbs free and entropy gets pushed to a side most of the time. Do those questions. If you have any doubts, if you have anything to ask me next week. We can take a, let's say, last hour of the class and discuss some questions if you have any questions. Okay, so next week also we'll have the same setup, but we will reserve the last hour for questions. Okay. Alright everyone, that'll be all for today. I'll be seeing you again next week. What are you going to do when you go home? Not today, don't do today. Next week, before you come, try to do as many questions as possible before you come. Okay? Alright, have a good night then.